what the theorists at Princeton explained to Penzias and Wilson was, well, look, if you go back far enough in time, then if there's any photons at all in the universe, they must have been much closer together. So if you go back in time, that means blue shifted. So they must have had much shorter wavelengths, much higher frequencies. In fact, they might have they might have had such a high energy that they had enough energy to ionize hydrogen. In other words, if they had, remember it takes a 13.6 electron volts, a photon that has that energy will split apart a proton from its electron. And if you have lots and lots of those photons, the entire universe would be ionized at any time before that in the Big Bang when things were hotter and closer together. Why is that important? That means that the universe went through a transition from being a very hot, fully ionized universe to cooling off so that the electrons could get back together and stick without being disrupted by a high energy photon and make neutral hydrogen. You went from an early universe filled with free electrons to a later universe which was filled with neutral atoms. So in a rather short time, all of the free electrons in the universe disappeared. Why is that important? Because the free electrons in the universe scatter light. Thomson scattering, it's something that you're supposed to have covered in your astrophysics class, was a very high density of these electrons just before the combination event that made everything become neutral. And so just before this, the optical depth to any kind of photons, it doesn't matter what the wavelength is, was enormously high. Literally, the universe was opaque to photons, opaque to radiation. So, of course, it was full of photons because it was very hot. So it was a perfect example of thermal black body radiation, completely opaque. And then all of a sudden it became transparent. In a very short amount of time, photons that had been bouncing around furiously like crazy in a meaningless random walk, suddenly it cleared, and whatever direction the photon was going on at that moment, it just went straight for the next 13.5 billion years until some of them landed at the Holmdel radio telescope in New Jersey. It's said to be the heat or the radiation from the Big Bang. Technically, no. It's the heat or radiation from an early time in the Big Bang, the time when the universe cooled down to about 3,000 degrees. Now, you can use our formula for what this time would be if you start with the temperature of the photons today, which is a very, very low temperature, 2.73 degrees. It's a simple thing to extrapolate how much smaller the universe had to be, how much shorter the wavelengths had to be, until that 3-degree radiation was 3,000-degree radiation. In other words, what I'm asking you, so what were they looking at? They were not exactly looking at the Big Bang. They were looking at what the universe looked like at a redshift of about 1,000. Well, actually, 1,100 if you want to be precise. There are no galaxies there. There are no stars. There's very little structure at all when this universe became transparent. You can work out what the age of the universe was. This is about 380,000 years after the Big Bang. That's an enormous extrapolation of those cosmology equations that we've gone through to, as I said, a time when every dimension of the universe, height, width, length, was 1,100 times smaller. So I guess the densities of everything were about 1 billion times higher than they are today. 3,000 degrees sounds a bit low energy for the photons. I mean, most of those photons don't have 13 electron volts. So how was it that even at such a low temperature, the universe was still completely ionized by this radiation? The answer is a little bit subtle, but it basically comes from the fact that there were so many photons, and it only takes one photon to ionize a hydrogen atom. So basically, there were billions of photons for every hydrogen atom. And of those billions of photons, a few of them are in the exponential tail. Remember, it's a Boltzmann distribution, which has exponentially few very high energy photons. But it doesn't, it only takes one of them. So you have a somewhat unexpected situation that the universe actually had to really cool quite far. It had to cool down to about 3,000 degrees before those poor fragile atoms could just hold together as neutral atoms, before the electron wouldn't be smacked apart by one of those high energy photons coming around. And as I said, it happened fairly suddenly. I think it happened from basically between a redshift of about 1200 and a redshift of 1000 was all done. Another very important thing which they were looking for and was discovered by some other people, the possibility of our motion with respect to the microwave background. The microwave background giving us the first definition of what the absolute rest frame of the universe would be, for someone who has no peculiar motion, going with the flow. The microwave background photons define the flow. This is an all sky projection. This is a very high contrast picture that's enormously blown up here. So you can see basically just about, it's like, I think 2 parts in 1,000, slightly hotter microwave background in this direction, roughly the direction of the constellation of Leo. That 1 or 2 parts in 1,000 cooler in the opposite direction. That is a dipole pattern, and that, like I said, is caused by the fact that we on Earth here, or we in the Milky Way, are actually moving. Not a shock. We have a small peculiar velocity with respect to the universe, and the reason is that there's a somewhat higher overdensity of nearby galaxies in this direction than an underdensity of them here. So we've been accelerated by this a little bit of anomalous excess gravity over here. Of course, on large scales, we're still assuming that the universe really has a uniform gravity, uniform mass density, and that we can ignore these peculiar velocities. But on a small scale, it's about 600 kilometers a second, which is not very much compared to the velocities of most galaxies. But there it is measured with great accuracy for the first time. After we remove the dipole, can we find structures, clumps, overdensities, or extra regions of a little bit of excess hotness or a little bit of excess coolness, temperature fluctuations, because we're looking back now at the universe when it was quite much younger, only several 100,000 years after the Big Bang. So here's the question: how uniform was the universe? Answer: much, 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 much more uniform than today. Terribly uniform, but not perfectly uniform. So let's remove this dipole pattern here and then look at what's left. Instead of having one of these projections, I have a beach ball projection here of it, which is kind of cool. These are the WMAP results with the dipole removed. And then that was already contrast enhanced. Now I'm going to ridiculously enhance the contrast. So we're looking now at about just a part in 100,000. So the hottest excess temperature microwave regions here are only 1 or 2 parts in 100,000 times hotter or denser in radiation than the coldest regions of the sky here, these little blue blobs, very close to being perfectly uniform. These, of course, turn out to be one of the most important findings in all of observational cosmology. So I want to spend a minute on it. It's super important for several reasons. First of all, of course, there had to be some density inhomogeneities, even though these are very subtle, just excesses of 1 part in 100,000. But there had to be some density contrast for them to eventually grow so that the dense parts would grow through the gravitational instability to become galaxies. We would not be here if there weren't these original inhomogeneities present. There had to be something which could eventually grow up in several billion years to make galaxies and eventually make stars and planets and people. We are extreme density inhomogeneities that have grown up, apparently entirely caused by the gravitational attraction of lumps of dark matter. We're looking here basically at the overdensities of dark matter early on in the universe. So that's one very important point. A second interesting question is, why? What must have happened earlier in the Big Bang that produced these irregularities? Could there be an explanation of it? Could that naturally have been predicted by something? It certainly wasn't predicted. None of this was really predicted very well. So that we'll get to that in the last lecture. And then the third question is, if you look at this beach ball here that shows the microwave back, stare at this thing long enough and you'll notice, do you notice a pattern? There's quite a lot of little blobs that seem to me to be around the same size, around about 1 degree across. There seems to be a lot of character structure. Yes, there's larger blobs here and so on, but there seems to be an awful lot of little blobs. These little blobs correspond to overdensities. If there's an overdensity with a characteristic size at the time of the microwave background. Oh, by the way, what is this time, this epoch that we're looking back to? I could say just a redshift of 1100, a redshift of 1100, when the universe, when the microwaves were 3000 degrees hot. That was the temperature of the universe. I could say that. But what's often described here is this is the era, the time of recombination. But this was the first time it had ever happened, ever, in cosmic history. In the Orion Nebula, it's going on all the time. Recombination radiation, it's happening, thousands of times a second. But I really think this should be called combination. I really think this, because this is the first one. It's not re. Re sounds like it's going on and on many times. The universe had only been around for about 400,000 years. At the time we're looking at it here, you can't travel faster than the speed of light. Photons do travel at the speed of light. So if you had a region that was a little bit hotter or a little bit colder, you would think that the region must have been in causal contact before the universe got to be 380,000 years old, so that everything in that region knew, could exchange energy, could exchange photons, could exchange heat, so that they all knew what temperature they should be, at least in that region of the universe. They wouldn't have received any photons, and if they didn't receive any photons, they sure didn't receive any other information. Nothing travels faster than light. They didn't receive energy, they didn't receive heat. They didn't have any knowledge of any other regions that were outside of their event, outside of their horizon. This leads to a number of fascinating questions then. It looks like what we presumably are looking at here is a number of little regions which are roughly within their own light horizons at this early stage of the Big Bang, when it was only 380,000 years old. So that leads me then to a question: how big a region was causally connected? In other words, what was the horizon of any region of the universe that could be in causal contact, that could transmit photons back and forth, transmit energies at the time of recombination? And you already have probably a pretty good idea of that, but I think I'll give you the actual formula. Where I'm going to go with this is I'm going to work out what the size of these horizons, these causally connected regions is. I'm going to give it to you in light years. Okay. Then I'm going to say, that is sort of like a ruler. That's how big the causally connected regions, or the horizons, were during the Big Bang at that time. Here's the money question: how big do they look today? Because the universe, of course, has expanded enormously by a factor of 1100. So how big a region of angle on the sky do they subtend now? I want to use these little structures that are observed in the microwave background. These they're temperature fluctuations, but they also correspond to density fluctuations of dark matter. And I want to use those fluctuations in the size of the horizon as a ruler, a standard ruler. And then I'm just going to look and see what angle does the standard ruler appear up, as we observe it today on Earth. That is a measure of how the universe has expanded from a redshift of 1100 to today. In other words, I am proposing the first angular size test of cosmology for the angular diameter size. And it has this interesting property that as you go to very high redshifts, things stop looking smaller, even though they're further away and the photons took longer to get here. It's kind of an interesting effect because of this 1 plus z factor. What we'd like to find out here is this cosmic distance, which is really just r here. I need to know how that varies for each step of the way back from redshift 0 today, all the way back to a redshift of 1100. I'm going to use the horizon size. I'm going to plug it into my formula. So I'm going to measure this. We're going to measure this with a NASA satellite. We're going to work out in just a second here what this is. So I'm going to know what this is. I'm going to know what this is. I'm going to work out what the angular diameter distance to the cosmic microwave background is. And that, of course, is a function of cosmology. It's a function of the history of the expansion of the universe. So there's the formula. Okay, all of this stuff is worked out in the book, rather detailed book about cosmology by my former teacher, Malkan Longhair. And, it's way more details than you ever really honestly would want, unless you're going to specialize in this particular field of microwave background physics. He lays this all out in chapter 12 here. But the basics of it, if you want to know what the horizon is at any particular time in the universe, you start at the Big Bang, you integrate up to that time. In my case, I'm going to integrate up to 380,000 years. And you say, well, how far did a photon go in that interval of time? Well, in that interval of time, it's always going at c, the speed of light. So that's how much distance it traveled, c dt, in each little delta t interval. Wait a minute, there's more though, because those early steps, the universe was much, much smaller. In other words, we have to divide that by the changing scale factor here. This is the same formula we've had before. That's going to keep track of how big this region was. And then after the time has passed, we have to multiply it back by the scale factor at that time. If I set omega lambda equal to 0, I just ignore it for the moment, then the integral comes out fairly simple. Then if I make an approximation, I say, well, I'm actually interested in the horizon at a redshift. How big was the horizon at a redshift of 1100? So this is huge here. It's 1100. So I can ignore this. Forget about the 1 here. Well, in that case, I'm just going to have a square root of omega down here. That's a constant, omega naught, in the integral. And then the rest of this integral actually can be solved because you've got basically z to the 1/2 here times 1 plus z. And you throw in a trig substitution. You work out the integral from the Big Bang, which is infinite redshift, up to the redshift that we observe, 1100. And you get a fairly common, interesting answer. Of course, it's got to have this cosmological distance in it. If you look at this thing a little more carefully, what happens, for example, if the critical density is 1, and then this is just 1 here, then the Hubble time was 2/3 of the age of the universe at that point. Does this make sense? Well, if the universe wasn't expanding at all, after a time t, you would have received, the furthest you could have received photons would be a distance of 380,000 light years. However, wait a minute. You actually can see further than that because the universe has been expanding. So some photons that are actually further away, the universe was smaller then, meaning that when they started, they were closer to you. That's where this R of t factor comes in. And so that helps them. That's why this is not 1. So this is a fairly general result. Your horizon turns out to be 3 times the light traveled time. Why am I fussing about that? CT is 380,000 light years at recombination. That's just what you get from the redshift. 3 CT, though, is how far photons could actually travel and exchange information. So everything could come into a thermal equilibrium within a region which at that time was 3 times CT. If it's 380,000, I multiply that times 3, that's going to be about 1,000,000 light years, or a megaparsec is 3,000,000 light years, so it's about a third of a megaparsec. No region in the universe back then, at the time of recombination, that's larger than 1/3 of a megaparsec should have had time to be in causal contact with each other. They should, you might naively think, been physically separate. No knowledge, no information even about any region further away than that. That's what it was back at recombination. Remember, though, that was when the universe was 1,100 times smaller in each dimension. So by today, these causally connected region. It was causally connected at the time that the microwave started their free journeys to us. At the time of recombination, 380,000 years after the Big Bang, these regions have now grown up to be 0.3 billion parsecs, 0.3 gigaparsecs. One question is, wait a minute, the regions that I'm seeing in that microwave background map on different directions of the sky are currently today much further away than 0.3 gigaparsecs. So I have no explanation for why they're a similar temperature. How do they know that they were supposed to be in equilibrium with each other? They don't even appear to have ever had any causal contact because they couldn't have exchanged photons with each other. There's two possibilities. Either this is just one of the most amazing cosmic coincidences that all these different regions decided to start expanding. Said, I feel like I'm going to be 3,000 degrees today. I feel over here, I feel like 3,000. I feel like 3,000. All these regions that had no way of knowing what the other regions were doing, they all picked almost exactly the same number. I don't believe in a coincidence. Something's wrong with my assumptions about the early universe. I must have made a mistake there. Somehow they must have been causally connected. They must have been way, way closer together than our equations of cosmology have said so far. So that's the first thing that really makes you suspicious, and we'll solve that on the last lecture of this class. It also gives us a ruler stick. There should be regions that were causally connected, these density fluctuations, or everything in the horizon of the universe at that time was a little bit overdense or a little bit underdense, and they should have a characteristic size, which today is 0.3 gigaparsecs. So I've got my standard ruler. My standard ruler was a third of a megaparsec. Today, it's a third of a gigaparsec because of the expansion of the universe. So it all depends on what dA is, the angular size distance at a redshift z of 1,100. Well, you can plug in some numbers, and if you plug in the numbers for a matter-dominated universe, which is a fairly simple numbers, the angular size distance to the microwave background, it's about 14 gigaparsecs. The structures that we're looking at are 0.3 gigaparsecs. What does that come out to? Remember our formula delta theta? I have an L over a dA. L. That predicts what? At 1 part in 40? What units is the angle in here? It's got to be radians here. So if we've got something that's about a 40th of a radian, that corresponds to what angle would these little blobs in the WMAP picture be? How big would they sub 10 now? A little bit more than a degree, right? Because there's what, 58 degrees in a radian, and this is a 40th of a radian. So maybe, I don't know, 1.5. That was a prediction, and I think a lot of people were expecting that. And what is the most important line on this slide here? That is not what was actually observed. Significantly smaller by about a factor of 2. Instead of being larger than 1 degree, they're actually only about 3/4 or 0.7 degrees across. So that tells you the dA actual, As we're observing this now, this is the angular diameter test. The actual dA in our particular universe that we're in is more distant, large. It's a larger universe than what you would have thought if it was only matter dominated. So now I want to, that's the conclusion. Now let's look at the actual data. Let's not worry about an empty universe very much. I mean, that's obviously there's some matter in the universe. An empty universe, all the distances are very, very large now because there was no slowing down whatever at early times. I want to take something more realistic. A model here, which is a critical density universe where things have been slowing down. The expansion has been, R of t has been going as t to the 2/3 for a long, long time. Now it's been slowing down. What if, though, instead you have a large amount of dark energy, lambda, that's actually L is for lambda there, so that actually the universe has a total critical density not made up primarily of matter. It's not dark matter that's doing it. This one here, I should say, is dark matter makes the critical density, and you get these curves. But in this universe here, this is the universe that was favored by the supernova distances. It's actually dark energy which makes up most of the critical density of the universe today. And so that means that the universe is bigger at large distances. And so the entire discovery that got the Nobel Prize for those supernova 1A competing teams was based on telling the difference between this red line and this red line over here. You see, they are different. This is a logarithmic scale. When you get out to a redshift of 1, they're differing, I don't know, not by that much. I mean, even a redshift of 10, they're only differing by maybe about a factor of 2. Pretty subtle measurement that they made, and they had to find very distant supernovas at a redshift of above 1 to tell you that this is the correct model for luminosity distance, not this one, the luminosity distance test. Today, let's look at the angular diameter distance. Remember, the angular diameter distance doesn't increase at high redshifts that much because you get the 1/1 plus z factor in it. In fact, this is one of the funny things about the angular diameter distance. As you take a standard ruler, let's suppose that the standard ruler was 1,000,000 light years across. That's the size of these recombination regions, horizons. So you take a standard ruler of 1,000,000 light years across, and you put it further away. It actually, when you get to a redshift here, we can work out what that redshift is. This redshift is 5/4. It stops looking smaller. If it's more distant at a higher redshift, the angle it subtends on the sky actually gets bigger. And this is because the object, when it initially sent its photons from both ends of the ruler, was closer, and you have to take into account the expansion of space. You'll notice that if there was more dark energy and less matter, then that basically means more space at large distances. Look at the green curve. At a high redshift here, the green curve is like almost a factor of 2 higher than the matter-dominated one. So in fact, this continues up to a redshift of 1100. So we have an observational test, which is not just a very subtle test that you could try to do by precision measurements of supernovas, where you really have to get their distances pretty good. Instead, we have an angular diameter test. We can just go and look and see what are the size of the blobs in the microwave background at a redshift of 1100. Does it favor this angular distance or this angular distance here? And you really don't have to be very accurate. On the left-hand side, I'm showing you the actual observed power spectrum. So this is the fluctuations in the microwave background. You saw that in the original picture here. We just basically did a Fourier transform of this picture, just fitted sine curves to all of them. And we found that there is indeed, as your eye can see, there's a lot of blobs with a characteristic angular scale here, and it's less than 2 degrees. A lot of extra power in the angular spectrum of fluctuations in the microwave background. It's less than 1 degree. The peak is here at 0.7 degrees. It's very well determined. That's the characteristic size of the structures that were present, the horizons, at the time of recombination, because that's when these photons just finally got free and just went straight, just traveled across the universe. So that's the actual observations. Here are theoretical curves, and here is the main curve that I want to show you. I'm sorry, these graphs here are put in the multipole. If you remember from your E&M classes, you expand a Fourier series on a sphere into multipoles, starting with a monopole, then a dipole, then a quadrupole. Those are down here. And then you just get smaller and smaller regions. There's about 0.7 degrees right there. These data are overwhelmingly showing you is that the angular diameter distance test, as applied to the microwave background map, absolutely requires here zero curvature. You can't even have a positive curvature of like 0.15 or even a negative. That's a very small negative curvature because it moves the predicted power spectrum away from what's observed. What's observed is exactly right in the middle of this. So this is basically the beginning of really what they call precision cosmology. The fact that they could measure this peak so accurate. In fact, it's been measured even much more accurately. And this in one shot proves that we live in omega k, that's this curvature thing, of 0. We have to be in a case where omega lambda plus omega matter must add up to 1. There's no room for any curvature. It's got to be a flat geometry of space-time. Now there's more. This is more subtle arguments that I don't think I'm really going to go into, but how strong would those excesses of matter and radiation be? How strong would those density concentrations be? Well, it turns out you need to have some reasonable amount of baryonic material to concentrate itself. And if you have more or less baryons than what we've actually got, the strength of these fluctuations would either be too strong, like here's the actual observations. It looks like it's about 6,000 in these units of microkelvin squared here. So it's exactly right there. But if there's too much baryons, the strength would be larger, totally not observed. If there's too little baryons, the strength of these fluctuations would be weaker, less of them than observed. Simply looking at that pattern, the pattern of fluctuations of these little ripples, and these are very subtle, delicate ripples in the microwave background, but now measured very accurately. Simply looking at this pattern here tells you what the total overall geometric shape of the universe is, very accurately. It's a flat universe, 0 curvature, and it even tells you here that omega baryon is not 1 at all. In fact, omega baryon is coming out to be very, very small. But we're going to find a better way of determining that. We also have some other useful things here. We've got a very precise temperature for the radiation, and we have a beautiful spectrum of it. Okay, so the temperature is known to 3 decimal places. I think it's about 2.728 degrees. This is the best, most perfect black body spectrum that has ever been measured by astronomers. Why? Because there was almost a perfect thermal equilibrium between the electrons and the protons and the photons at the time of recombination, which is where this radiation has come from. And so, of course, originally, at the time of recombination, the sky was blinding light, visible light, like the surface of the sun, was dazzling, 3,000 degrees. However, it's now redshifted all the way down into the microwaves, but it still preserved its perfect black body shape. We now know precisely how many microwave background, or if you want to call them Big Bang photons, there are. And it turns out that there's an awful lot of them, although they are very low energy. Let's think about that. If you average over all of the universe, there's approximately 2 billion photons for every single baryon. That's really quite a large number. What about antimatter, like antiprotons? Early on in the universe, these photons were not just visible photons. It wasn't just 3,000 degrees. It was these photons had energies of GeVs. It corresponds to billions or hundreds of billions of degrees of temperature, not just 3,000 degrees. If you believe that we can play the tape of the expanding universe that far backwards, if you believe that our Big Bang equations are really valid, then there must have been a time when basically the photons had, or gamma rays, the universe was dominated by the energy of the sea of gamma rays, and of course colliding all the time. Every time two gamma rays collide, if they have an energy larger than the rest mass of a proton, there's a fair probability that two gamma rays, let's say they have 10 GeV of them, there's a fair probability that they might produce what? A particle and an antiparticle pair. These photons were producing pairs of protons and antiprotons, equal amounts of matter and antimatter. Then as things cooled off, all of the matter and all the antimatter annihilated very quickly, and now we're just left over with the survivors, which is matter. There's no antiprotons left. They're all gone. But what this number is telling us is in the early universe, when it was very hot and all of this matter and antimatter was being produced, there was almost exactly the same quantity of matter and antimatter. There was a slight preference, 1 part in a billion preference for matter over antimatter. There was a slight asymmetry in favor of matter there, and that's why we're here. Thank God for that. We don't know exactly how that happened, but it is physically possible. The laws of physics do not require that every reaction always produces equal amounts of matter and antimatter. It certainly is true of photons, but there are some more exotic reactions which were likely happening in the early universe, the early stages of the Big Bang. How early? I mean in the first second, before the first second. Some of these reactions had a very, very slight preference for matter over antimatter, produced a little asymmetry, which is crucial. Otherwise, we wouldn't be here because there wouldn't be any matter left in the universe. Today, the rest mass energy of a hydrogen atom is a proton. It's about 1 GeV. Today, the cosmic microwave background photons are pathetic. They're down in the millimeter range. So each one of them is, I don't know, like about 1/3000th of an electron volt. If you take into account the fact that there are 2 billion of these microwave photons for every hydrogen, then these get closer. Then they're only different, I guess, by about a factor of 3 or 4,000. It's a few thousand. And so then if you play the expansion of the universe backwards, play the tape backwards to a high enough redshift, these energies go up because now they're blue shifted. They go up by a factor of 1 plus z. So there's got to be a point back, it's actually before recombination, there has to be a point in the early history of the universe when it was so hot that the energies of the photons were so high that they exceeded the energy of mc squared, of all of the matter. Now, I'm even including dark matter in here also. The radiation was higher. So you can do an exact calculation. You have to include a number of things. But basically, above a redshift of 4,000, radiation was in control. It was the dominant form of energy. So then that was before recombination. The universe was less than 50,000 years old. Now, why am I telling you this? We have to go back to one of the cosmology results. What is the expansion rate of the universe in a radiation-dominated universe, where rho, the energy density of radiation, goes as 1 plus z to the 4th, or r to the minus 4, not like matter, the usual thing, which goes like r to the minus 3. So density of normal matter or dark matter, that goes as 1 plus z cubed. But at a high enough redshift, above 4,000, 1 plus z to the fourth wins out. So why do I have to say that? Because the universe was no longer expanding with r going like t to the 2/3 power. Remember the result? In the early stages of the universe, which is all what the Big Bang is about, this is all early stages, it was totally radiation dominated universe, we have to use r goes like t to the plus 1/2. That's your solution for a radiation dominated universe. And so that means that the temperature goes down as r goes up. So the temperature scales as 1 over the square root of time. And if you want to put it in some interesting units, scaled to today, so we have to take into account the actual expansion of the universe today. It turns out that if you write down what the age of the universe is, this is how much time since the Big Bang, and I do it in seconds. I know this is a crazy extrapolation. If I do this in the age of the universe measured in seconds, then, and I take 1 over the square root of that, then I will get the temperature of the radiation of the universe in units of 10 billion degrees, 10 to the 10 Kelvin. That's a lot of energy, isn't it? 1 second after the Big Bang, the universe is 10 to the 10 degrees hot. It's dominated by the energy of gamma rays. How high are these gamma rays? Well, if you convert 10 to the 10 degrees, that corresponds to about 1 million electron volt, an MeV gamma ray. Anything else have a rest mass? Any particles have a rest mass of around an MeV? If you take 1 electron and 1 positron, that has a mass of about 1 MeV, a rest mass. So before the first second, there were gamma rays capable of also producing electron-positron pairs. And again, they would have produced an equal amount of matter and antimatter. But after the universe cooled down to about 1 second, this process no longer happened because things had cooled off. The wavelengths had stretched out of these gamma rays that go to lower energies because of the expansion of the universe. And all of this matter, antimatter business was in the past. Wonder what kind of reactions could be happening back then. Well, it turns out that at temperatures of higher than 10 billion degrees, you have 2 reactions which are happening fairly rapidly. What I mean by rapidly is they're happening many times a second. I mean, the universe is only a second old at that point or less. But these 2 reactions in particular are very important to us. By the way, you've seen these reactions. Any other situation in the universe where we get temperatures of 10 billion degrees? This is like the inside of a supernova, although the densities are lower. And so you get these very interesting weak nuclear force interactions, the same as what we have in a supernova. Remember this one? An electron and a proton, that's a 0 total electric charge, can, by the weak nuclear force, can combine and produce a neutron. That's how a neutron star is formed in a supernova. And you get a neutrino out of it here, an electron neutrino. Or you could have the opposite reaction. A neutron could break up into an electron and a proton. You also have, by the way, the same kind of reactions going back and forth if there's any antimatter around. So for example, a positron can combine with a neutron to make a proton. Before 1 second, there's all these weak nuclear reactions. Basically, what are they doing? They're shifting continuously protons into neutrons and neutrons into protons. Back and forth, back and forth. It's just a soup. They do have quite similar masses. In the early universe, before 1 second, these weak nuclear reactions are pretty much going to guarantee that there's going to be about an equal number of neutrons and protons, because the reactions will just go back and forth, zillions of times a second. However, The reason I picked 1 second is that is a very pivotal, crucial time in the history of the universe. So far, we've got a number of like key calendar dates on the universe. Clearly, the formation of the first stable atoms, stable atomic hydrogen, for example, at 380,000 years after the Big Bang, that was an enormous, significant event. The universe went from being completely opaque in a fog of free electrons to being neutral and transparent at the epoch of the moment of the epoch of recombination. So that was a big date. Now I've got another big date. They're all getting squished down to very short times. I guess if you take the logarithms of these things, they're more uniformly spread out. But things were going really fast. At 1 second, the density of particles had dropped. The temperature of the gamma rays had dropped. The energies of particles had dropped. And the weak nuclear interactions, then the rates drop also. They drop rather suddenly. So effectively, rather suddenly, these very nice nuclear reactions, these weak nuclear force reactions, stopped. They shut off. No more conversion between neutrons and protons or protons and neutrons. So then you're asked, for every proton that was around by the time the universe was 1 second old, how many neutrons were around? Well, which one has more mass? Neutron has a little bit more mass. I think it's a little bit more by 1.5 million electron volts. That's a very small fraction, right? It's not, their masses are like 930 million electron volts. They differ by, what is it, about 1 part in 1,000. Does this look familiar? Is this the Boltzmann formula? A neutron has a little bit more rest mass energy than a proton. And so in a thermal equilibrium, which was established by these reactions, the Boltzmann distribution was established. It should have established this neutron to proton ratio until there was no more reactions to keep it going. And that happened right at around 1 second. So at 1 second, a lot of things happened when the weak nuclear reactions shut down. Well, two things in particular. First of all, the neutron to proton ratio just froze out. You can stick the numbers in here. If you put in 10 to the 10 here, you put in the energy difference here. Neutrons, well, I have to say there were quite a few of them. Of course, there's going to be less of them than the protons because neutron has more rest mass energy. Be about 20% of all the baryons there were neutrons. So we've got neutrons, we've got protons. They're no longer changing back and forth. We're now calming down to like, only billions of degrees here. That sounds kind of similar to the interiors of stars, where neutrons, if they're around, could have nuclear fusion reactions with protons. They have a high enough energy. They're well above the threshold energy for nuclear fusion reactions. So you're thinking, couldn't the entire universe, everywhere, all of space at that time, be taking its fundamental particles, which are now stable, neutrons and protons, and stuffing them together into fusion reactions to make more complicated nuclei? Shouldn't the entire universe, right around the time of 1 second, starting at 1 second or so, shouldn't the entire universe have been doing nucleosynthesis? You'd be right. It didn't have very much time to happen either, because after several minutes, the temperatures were cooler than the interior of the sun. The temperatures had dropped too low for nuclear fusion reactions to take place. But a lot of very interesting stuff was able to happen in the first 300 seconds of the Big Bang nucleosynthesis, 5 minutes that changed the universe. And we're able to now search for the leftover remnants, the fossil leftover clues from that Big Bang nucleosynthesis to test whether our view of the Big Bang, our view of cosmology, our view of particle physics, to test if it's correct or not. And amazingly, we're going to learn even more stuff. guess you know it's going to turn out to be correct, but it's going to turn out to be incredibly informative.